Hello students, welcome to EPG Pathshala on quantitative methods in geography. I am Aslam Mahmood, a retired professor from Jawaharlal Nehru University. Today's topic of discussion is test of significance based on small samples and basics of analysis of variance. Friends, see, we enter when into the statistical analysis, we have two options with us. Either we have the data from the census enumeration or from the sample surveys. When we have census enumeration data, we get the information about the whole universe about which we are talking, and we don't need any further help for sampling theory, etc. However, when we go for a sampling exercise, instead of the universe, we get the data only a part of the universe. But when we study the part of it, part of a universe, our conclusions or our understanding does not remain only limited to that sample part of it, because that sample part is a very small part of the universe and has been chosen for our convenience. Our main concern always remains the universe. Therefore, we have to learn how to draw inferences from sample to the universe. The moment we enter into the exercise of drawing inferences from sample to universe, we have to take the help of various tools and techniques in statistical theory. One of the important tool is the theory of probability, the other is the theory of sampling. In the theory of sampling also, we know that a sampling distribution of mean of large sample of size, say n is equal to or greater than 30, drawn from any universe with known mean, that is m, and a known standard deviation, is found to be normally distributed with mean equal to the value of the universe mean and the standard error as standard deviation divided by under root n, as described in earlier module on the test of significance based on large samples. However, when the size of the sample becomes less than 30, we do not apply the findings or the properties of the large sample test. We have to enter into something known as theory of small sampling theory. We know that sampling distribution of mean will be normal if the size of the sample will not be normal if the size is less than 30. For a small sample, the size of the sampling, for a small size, the sampling distribution of means drawn from a normal universe will acquire another type of distribution known as student's t distribution. Sampling distribution of means or t distribution will be flatter than a normal distribution. For t distribution, 1% or 5%, the limit will not be as in the case of normal distribution 2 times or 3 times of the standard error. It will be more than these values, and the size of the sample will become, as the size of the sample will become smaller and smaller, the limit will become further larger and larger. It will not give any fixed limit. Even every sample size will have different limiting values for different levels of significance. So, they will change not only with the size of the sample, but as in the case of normal distribution, with the level of significance also, the limits will keep on changing. The sampling distribution of all the possible values of means and standard deviations are not possible to study. William S. G. Gauss, the noted statistician, has standardized them by taking the ratio of the difference between the sample and population mean to its standard error. And has worked out limits for different levels of significances. These values have been tabulated for different values of the size of n minus 1, known as degrees of freedom, where n is the size of the sample. Since then, the ratio of the difference between sample mean and universe mean is to its standard error is being to test whether a given sample mean can correspond to a universe mean or not. The test is known as student's t-test. The test is named after Gauss, the noted statistician, after him, as he used to write under the pen name of student. These values have also been published in statistical tables for biological and medical research, edited by R. A. Fisher and F. Yates, popularly known as Fisher and Yates table. These tables are available in appendix of almost every book on statistics. With the increase in the sample size, the sampling distribution of mean will keep on approaching to be normal, and for degrees of freedom equal to or more than 30, the sampling distribution of mean converges to normal distribution. Now, student t-test has two different approaches. One is for one sample test and the other is meant for two sample tests. We will discuss first when we have only one sample. If a small sample of size less than 30 is drawn from a normally distributed universe, remember here that the universe from where the sample is drawn is to be normally distributed in the case of t distribution. In the case of large sample, there was no restriction on the nature of the distribution of the universe, but in the case of a small sample, the universe from where the sample is drawn has to be normally distributed with a given mean m and standard deviation as sigma. The sampling distribution of the ratio t, which is modulus value of difference between sample mean and the population mean divided by the standard error, standard deviation divided by under root n, which is the standard error, will follow t distribution with n minus 1 degrees of freedom. Note that numerator of t is a modulus and the sign of two vertical lines, that is 1, 1, indicates a modulus value. In general, the standard deviation of the universe is not known, because if standard deviation is known, that means we know everything about the universe. So, it is not known. In such cases, we estimate it from the standard deviation of the sample only and use a slightly different formula given below, which is t is equal to the difference between the sample and the population mean divided by sigma upon under root n minus 1. Earlier, when in place of standard deviation, we know the population standard deviation, we use the sign under root n. But here, if it is not known, we replace it by the sample standard deviation and divide it by under root n minus 1, where sigma is the standard deviation of the sample. Using the above mentioned properties of t distribution, we can test whether a sample mean m could have a population universe mean m or not. We make a null hypothesis denoted by H0 that a given sample mean m can have a proposed universe mean capital M, and test it against an alternative hypothesis denoted by H1, that is, the sample mean m, small m, does not suggest that the universe mean could be capital M. More precisely, it can be written as given below. Null hypothesis, modulus value of capital M minus small m is equal to 0. as against the alternative hypothesis, modulus value of m minus capital M minus small m is not equal to m. The null hypothesis would be that modulus of capital M minus small m is equal to 0. That is, m is equal to m, capital M is equal to small m, as against the alternative hypothesis, that is, modulus of capital M minus small m is not equal to 0. That is, capital M is not equal to small m. Under the null hypothesis, the calculated value of t statistics will be as shown here. If the given sample meets the proposition of the null hypothesis, calculated value of t should be less than or equal to the tabulated value of t at 5% or 1% level of significance for n minus 1 degrees of freedom. In such a case, the difference between proposed m, that is capital, and the observed m, that is the sample mean, that is the difference between capital and small m, will be considered as insignificant at the given level of significance, and the null hypothesis will be accepted. In case the calculated value of t ratio is found to be more than the tabulated value, the difference is said to be significant at the given level of significance, and the null hypothesis will be rejected and the alternative hypothesis will be accepted. That is, alternative hypothesis is that capital M is not equal to small m, or modulus value of capital M minus small m is not equal to 0. The absolute value of t ratio should not exceed the tabulated value of t for n minus 1 degrees of freedom. These table values are given in annexure for few level of significance with this module. In most of the cases, we choose these values for either 1% or 5% level of significance, as level of significance more than 5% or more than 10% will mean a higher level of probability of error. It is also to be noted that the rejection of the null hypothesis that modulus value of capital M minus small m is equal to 0 at say 5% level of significance will mean that the given sample mean m suggests that the universe mean cannot be considered as capital M. It could be more than m or could be less than m. Since the probability relates to either of the two events, it could be 2.5% for less and 2.5% for more, and we call it a two-tailed test. If we take only one possibility, say universe mean could be more than m, its level of significance reduces to half, and the test will be known as one-tailed test. Thus, the same value of t for two-tailed test at 5% level of significance will correspond to only 2.5% level of significance in one-tailed test. One can verify the above point from the limiting value of t test given in annexure. If the calculated value of t exceeds the table value, the absolute difference between sample mean and universe mean, that is m minus capital M minus small m, is said to be statistically significant, and so the null hypothesis is rejected, and we conclude that the universe value of the mean could not be considered as capital M. In case the calculated t value is less than or equal to the table value of t, it is considered as insignificant and the null hypothesis is accepted, that is, we conclude that the universe mean may be equal to capital M. Now, let us show it by taking an example. Agriculture productivity of farms of a given region is normally distributed over a space. A random sample of 10 plots is drawn and their productivity X in terms of 1000 rupees per acre is found to be like given here. Does the data suggest that the mean productivity of the universe could be 20500 per acre? In the present example, m is equal to, I have worked out the value of the mean, is found to be 20.5 thousand rupees, 20.5 thousand. The value of standard deviation is given, which can be is not given, which can be estimated from the sample as sigma. Sample mean m also will be worked out from the sample values as shown below. You see here in the table we have shown the calculation of computation of the sample value of the mean and sample value of the standard deviation. Sample value of mean is equal to 182 100 per acre, and sample standard deviation is found to be 581.5 divided by equal to 20.104. Now, the tabulated value or computed value of t would be the ratio of the population mean minus sample mean divided by sample standard deviation and divided by under root n minus 1, which comes out to be 2.862. The table value for t for 9 degrees of freedom. 9 degrees of freedom means n minus 1, n in this case is 10, 10 minus 1 is 9. The table value of t for 9 degrees of freedom is found to be 2.26 at 5% level of significance and 3.25 at 1% level of significance. Now, we see that our computed value is more than the 5% level value, tabulated value, but less than 1% level of value. So, we note that it is significant at 5% level of significance, but if we take 1% level of significance, it is not found to be significant. It is only significant at 5% level of significance. Explanation. Now, this when a given value is found to be significant at 1 and not significant at other level of significance, this can be explained in the context of the above example. The result of t test given above shows that the null hypothesis of the mean productivity of the region, the universe, could be 20500 per acre can be rejected with 5% probability of error only. That is, it is significant only at 5% level of significance. However, if we want to be more accurate, we have to accept the null. We should not reject the null hypothesis. We should accept it as it is not significant at 1% level of significance. It is insignificant. So, we accept it at 1%. That means, if we do not want more error, we should not go for rejecting the hypothesis. We should accept it, and we can, if we reject it only, we carry some amount of risk of error, that is the 5%. Now, here I have shown you how we can use a t-test when you have one sample, and against that one sample mean we have a population mean, a proposed population mean, and we see whether the difference between the sample mean and the population mean is significant or not. We may have two universe, two populations, and we draw two samples from each universe with the question in mind that whether the two universe have equal mean or not. So, in the above case, we had one universe which has normal distribution from where a sample was drawn. Another important situation in which t-test can be helpful is when we have two universes both normally distributed and have common variance. This common variance is something very important to know, that we have two universes which may differ in terms of their mean, but should not differ in terms of their variability, and they should have a common mean, common variance, whose mean values are not known. With the help of the sample means of the random samples drawn from each universe, we can test the null hypothesis whether the universe means are equal or not. Thus, if two small random samples of size n1 and n2 are drawn from two normally distributed universe, suppose R1 and R2 with equal mean M1 and M2. Here we are presuming that they have equal mean and common variance. The sampling distribution of absolute values of the two means, that is M1 minus M2, will follow the t distribution when the t ratio is given as shown here. Here t is equal to modulus of the difference of the two mean divided by s into under root 1 upon n1 plus 1 upon n2, where s is the common variance, common standard deviation, or common s square will be the common variance. With n1 plus, this statistics will be distributed as t distribution with n1 plus n2 minus 2 degrees of freedom. Also, S is the pooled estimate of the common variance of both the universe. If S is a common variance and a common standard deviation, and F is not known to us, we can also estimate it from the sample standard deviations, as was the case earlier also. From the two standard deviations, we work out a common standard deviation by pooling them, and we use the formula given here, that the pooled estimate of the common standard deviation is equal to standard deviation square, that is variance is equal to summation of the values of the first sample minus their mean and square all the values and add them, plus summation of all the values minus of the second sample minus their mean and square them, and we add all such square and add all such differences. The summation of the two such sums is divided by the common size of the sample n1 plus n2 minus 2. This will give you a pool estimate of S square, which is the common variance of the two samples. In two samples case, the null hypothesis would be that two universe mean capital M1 and capital M2 are equal. That is, M1 is equal to M2, against the alternative hypothesis that M1 is not equal to M2. The procedure of testing the significance of t would be almost same as was in the case of one sample given above. We have to calculate the t ratio as defined above from the sample data and compare it with the tabulated value t for n1 plus n2 minus 2 degrees of freedom. Earlier degrees of freedom were n minus 1 because there was only one sample. Now, since there are two samples, it would be the summation of their number of observation minus 2. Now, before applying to t tests to two samples, we have to test the equality of the variance of two universe also from this sample variance with the help of F test. See, basic assumption to start with was that the two universe have equal variance. Now, the t-test will be applicable only when this assumption is true. Now, this assumption can also be tested by taking the two sample standard deviation or variances with the help of f-test. If S1 and S2 are two independent sample estimates of the variances of two normal populations, where S1 square is as shown here and S2 square is shown here, and we denote the larger value of S as S1 so that S1 is greater than S2, then under the null hypothesis that their population variance may be same, the f-test is the ratio of S2 and S1 square and S2 square will be used here, S1 square divided by S2 square, with degrees of freedom being n minus 1, comma n1 minus 1, comma n2 minus 1. F ratio gives a distribution which varies according to the numerator degrees of freedom n1 minus 1 and the denominator degrees of freedom, that is n2 minus 1, indicated in the parenthesis with f values like f values. The values of the f ratio are also given in appendix of almost every book on statistics. These values are borrowed from Fisher and Yates ratio tables referred above. Now, the whole thing, the two sample tests of significance, again we explain in further detail by taking an example. We can apply t-test as given above only after ascertaining that the variance of two regions R1 and R2 are same by testing the significance of the ratio of the two sample variance, S1 square and S2 square. F-test. For testing whether S1 square and S2 square are insignificantly different from each other or not, we use F ratio test. Computation of these two sample variances is carried out as given below. We get the mean of the first sample as 2 and mean of the second sample as 1.4. In the second step, we work out deviation of each value of sample 1 from its mean value and square them and add all those deviation, and this addition is found to be 0.32. We similarly find the summation of the deviations from the mean in the case of second sample, which is found to be 0.2, and S1, that variance of first sample can be worked out by dividing the sum of the squares of the deviation by the number of observations minus 1, that is 0.32 divided by 8 minus 1, that is 7, which is equal to 0.457. Similarly, for the second one, S2 square is found to be 0.0222. F ratio would be the ratio of the two variance values, which is found to be 2.0587 for 7, 9 degrees of freedom. 7 corresponds to numerator and 9 corresponds to the denominator. Corresponding tabulated value for 7 and 9 degrees of freedom at 1% level of significance is 5.47. So, our calculated value of f is much lower than the tabulated value, hence it is insignificant at 1% level of significance, and we conclude that the two regions may have equal variance. Now, once the equality of the variances of the two universe has been established, we can go for the t-test. In the t-test, the null hypothesis would be the average yield of wheat per acre in two regions is equal. Against the alternative hypothesis, average yield of wheat per acre in two regions is not equal. Now, pooled estimate, since we have found that the variance of the two samples are insignificantly different. We can find out a pooled estimate of the variance of both the universe, which is given here and is found to be 0.182, and the T ratio then can be computed by taking the modulus value of the difference between the two sample means divided by the pooled estimate of S, that is the standard deviation of the two universes is 0.1802 divided by under root of 1 upon n1 plus 1 upon n2, that is 1 upon 8 plus 1 upon 10, which the ratio is found to be 7.02. The tabulated value of T for 16 degrees of freedom at 1% level of significance is 2.92. As our computed value of T is 7.02, here it is found to be much higher than the tabulated value, our limiting value 2.92. Thus, T value is statistically significant at 1% level of significance, suggesting that the two regions R1 and R2 differ in terms of their universe mean. Note that if a T value is significant at 1% level of significance, it will be automatically significant at higher level of significances also. So, there is no need to check its significance at 5% level of significance. Friend, this completes my discussion on the test of significance based on small samples using the t-test for one sample as well as for two sample problems. I hope you enjoyed it, and we will meet on some more such discussions. Thank you very much.